Welcome to Shanti-Peace for Mathematics. In my previous two videos, we have learned regarding a vibration for infinite string and semi-infinite string, and we have solved the wave equation using that conditions. Here in this video, we'll talk about the solution of a wave equation, or I can say a vibration of a string of a finite length. That means we have a string which is given, which will be fixed with the two ends, and we'll consider the one fixed end, it is x is equal to 0, and another fixed end is x is equal to L. That means the length of the string is L, and we'll make some motion into this string, and we need to find out what will be the displacement, that is y, what is the position of x and at any time t. So that problem of vibration of a string for finite length for wave equation is described in this manner. The governing equation of the wave motion of a string is defined like this. And there are initial conditions is there. That means when we'll starting the problem, that means at time t equal to 0, we'll consider the displacement is u of x and the velocity is v of x. And there are two boundaries we have. So at the boundary, that means x is equal to 0 and x is equal to L. They are the two boundaries of this string. And in that, we'll consider the velocity and the displacement is 0. That means at this both the boundary conditions, we'll consider the displacement is 0 and the velocity is also 0 for any time t. Now, the objective of this video is to discuss the solution for this type of problem. We have already derived the solution of infinite string for the same problem using D'Alembert solution. So let us recall what is the D'Alembert solution is. So the D'Alembert solution for infinite string is stated like this. That means we have a wave equation and your string is given into the infinite length, and if you have a two initial conditions, that is y of x0 is f of x and velocity is g of x, then this solution is known as a D'Alembert solution. Here for finite length also we are solving our problem using this D'Alembert solution, but for that we need to reconstruct or we need to extend our data for infinite length, because here whatever the data it is given, that is these initial conditions are given only for this intervals, that is 0 to L. So we need to extend this function u and this function v for infinite intervals, and that can be done using the periodic function. So we'll define a new function to construct the solution for this finite length problem. For infinite, using infinite length problem, we extend this function u and v as in this manner. So we'll define u of x is equal to small u of x if your x is between 0 to L, and it is minus of u of x if the value of x is between minus L to 0. That means we are defining a new function u, which is an odd function. With this odd function is actually 2n L, so it is actually a periodic function. That means after the period 2L, the values will be repeat, where your x is between minus L to L and the value of n, it is from plus or minus 1, plus or minus 2 up to so on. That means it is an integer. Similarly, v also can be defined. V of x is also can be defined using the odd function in the same manner. That is v of x if the value of x is between 0 to L, and minus of v of x if your value of x is between minus L to 0. With v of x plus 2nl, that means the function v is also an periodic function for all values of x between minus L to L, and n is equal to plus or minus 1, plus or minus 2, and so on. One should note that this u and v functions are periodic odd function with the period 2L, and they will obtain the value in the interval 0 to L, it is u of x. So we'll write that is as a statement that we observe that u of x and v of x are odd periodic function with period 2L, and they'll contain the value into the interval 0 to L is u and v with respect to u and v. Now, since this capital U is a 2 pi periodic function, then it is expanded as a Fourier series, because whenever you have a 2 pi periodic function, we can find out the Fourier series of such function. And let us recall what does it mean of a Fourier series. So let us assume that u of x can be expanded as a Fourier series. That means u of x is equal to summation n running from 1 to infinity an cos n pi x upon L plus bn sine n pi x upon L, where this an is 1 upon L minus L to L fx, but fx is actually u of x. So that is u of x cos n pi x upon L dx. Bn will be 1 upon L minus L to L u of x sine n pi x upon L dx. But this value of an will be 0, as we know that a sine is an odd function and u is also odd function. So odd into odd function will be the odd function, and hence this quantity, that is this bn, will change to 0 to L 2 times u of x sine of this. But this an, where this u is odd function, cos is an even function, and we know that the odd function into even function is an odd function. So that means the integral is from minus L to L, it is an odd function. So that's why this a is 0. So what is the conclusion we can make it out of this? This Fourier series, that means what we can write down is u of x is equal to summation n running from 1 to infinity bn sine n pi x upon L, where the value of bn we can write down, that is 2 by L, it is 0 to L. It is actually capital U, but in capital U is small u in the interval 0 to L. So that's why this will gives me small u of x sine n pi x upon L dx. So this will be the value of u which you can obtain, capital U. And similarly, the same concept and similar way we can do it for v also. So v of x is gives you summation n running from 1 to infinity bn dash, because this bn is also already used here, so I just use the bn dash, will be sine of n pi x upon L, where bn dash is equal to 2 by L integration from 0 to L v of x sine n pi x upon L dx. So this will be the value of u and v we can get for this initial conditions which we have here into the D'Alembert solution that we have here. Therefore, the D'Alembert solution we can write down, that is y of xt is equal to 1 by 2 u of x minus ct plus u of x plus ct plus 1 upon 2c integration from x minus ct to x plus ct v of s ds. Now just observe that what is u of x minus ct and what is u of x plus ct. If I substitute the value of u here, that the value of u is this, instead of x we need to use the x minus ct and x plus ct here. So for that, just simplify this quantity separately. So now 1 by 2 u of x minus ct plus u of x plus ct, if I substitute that value, that is 1 by 2 as it is, summation of n running from 1 to infinity bn sin n pi x upon L. Instead of x we have it is x minus ct, so it is x minus ct plus summation n running from 1 to infinity bn sin n pi. Now instead of x we have it is x plus ct divided by L. So this will be the value you have. Now this summation I will take together, bn will be common out, and this 1 by 2 is multiplied to the both this summation. So that's my, we'll have in the next one, it is 1 by 2 u of x minus ct plus u of x plus ct is equal to 1 by 2 is common out, and in the summation we'll have summation n running from 1 to infinity bn, inside bracket we'll have it is sin n pi x minus ct by L plus sin n into x plus ct by L. So this is the things we got for plus sign. And now s plus s, we use the formula for s plus s, that is will gives me 2sc. So that 2 will adjust here, so that 2 will be cancelled out, and so the finally you will have it is 1 to infinity bn sin, this will be the a, this is b, so we are using actually formula for sin a plus sin b is equal to sin 2 times sin a plus b by 2 cos a plus b by 2. We are using this formula here, and using that we'll have it is sin a plus b, that is n pi L is common out, we'll have it is x minus ct plus x plus ct divided by 2, but this minus ct and plus ct will get cancelled out, we'll left with the 2x, and that 2 is adjusted with this 2, so you will have it is n pi x upon L into cos, now it is a minus b by 2, so that is x minus ct minus x minus ct, so that's why this minus x will get cancelled out, and minus ct and this minus ct will become plus ct, and this minus sign will be absorbed by cos, so that's why we'll have it is n pi ct upon L. So this will be the value of 1 by 2 u of x minus ct plus u of x plus ct we get. So in this D'Alembert solution we'll have this side, now we'll need to calculate what will be this thing, that is 1 by 2 c integration minus x minus ct to x plus ct v of s ds. So for that let us see, now calculate 1 by 2c integration from minus x minus ct to x plus ct v of s ds. 1 by 2c, as we know that the value of v of s that we have calculated here, that is summation of bn dash sin n pi x upon L, where bn is this, so that is we'll substitute x minus ct to x plus ct, this summation of n running from 1 to infinity bn dash sin n pi s upon L ds. So integration and this summation will be interchangeable because the Fourier series is uniform conversions, and under the uniform conversions we can interchange the summation and the integration sign. All sort of the mathematical analysis we are using, and we are assuming that all the things is satisfying here, and that will gives me summation running from 1 to infinity x minus ct to x plus ct. Bn dash is also independent of x s, so that's take out sin n pi s upon L ds, and then we'll take this integration will gives me 1 upon 2c summation n running from 1 to infinity b and s will gives me integration of this sine, it is cos. So that's why it is cos. And if I substitute this limit, that is, first we'll substitute x plus ct in place of that. So it is n pi x plus ct divided by L. Then it is minus cos, and the integration of sine, it is minus sine. So that's minus I will take out, and that is n pi x minus ct upon L. Two will forgot that by dividing by this n pi upon L. That is the constant we have here. So when we integrate this, we'll have in the denominator it is n pi L. So it is n is depends on n, so that's why we'll write that n here, and that pi we can write down, it is here pi upon L. L is goes in the numerator. Now we'll use the formula, it is c minus c, it is minus 2ss, and this minus 2 is adjust with this minus 1 by 2. So this minus 2 is cancelled with it minus 1 by 2, and then we'll get it is integration of this quantity, it is L upon nc, that is summation n running from 1 to infinity b n dash upon n, that is this quantity. Now here we are applying this formula, that is c minus c, so that is sine of n by L into x plus ct plus x minus ct. So this x plus ct and minus ct will get cancelled out. We'll left with the 2x. So we can have, that is sine n pi x upon L into sine, when we have it is a minus b, that is, this is a, this will be b. So it is x plus ct minus x plus ct. So that means this x will get cancelled out and ct will be left. So therefore it will gives me the sine of n pi ct upon L. So this is the value of this integration, and therefore the solution y of xt becomes, by putting the value, that is y of xt is equal to, first we have it is this value, that is u of x minus ct plus u of x plus ct, and that value we have included, it is this, that is summation of bn sine of n pi x upon L cos of n pi ct upon L. So that's why we can have, that is summation of n running from 1 to infinity bn sine n pi x upon L cos n pi ct upon L plus the other things which we have here, it is 1 by 2c integration of this, and that value we have calculated here, and so that will gives me L by pi into c summation n running from 1 to infinity bn dash upon n sine n pi x upon L and sine n pi ct upon L. And we should actually check that this y of xt, it satisfies our initial as well as the boundary conditions, and that is easily seen. Check whether this boundary conditions and initial conditions are satisfied or not. So when x is 0, then y of 0t, that means sine is 0 here. If I substitute x is 0 here, that means sine 0, and sine 0 we know it is 0, and here if I substitute sine in place of x, if I substitute here, then it is also sine 0 on this summation. So it is 0 plus 0, so we'll have it is 0, and we differentiate this with respect to t, then we should need to check that all the conditions of term by term differentiation is possible, and that is there because it's everything is contained in sine and cos, and it is sufficient condition for this u is a twicely differentiable function and the third derivative is the piecewise continuous. All sort of conditions are satisfied, so we are able to make a differentiation of this with respect to t. And if you can do that, and if you substitute in that also sine x is equal to 0, then it will contain sine function, and the sine function will have a 0 at x is equal to 0 there. So that's why you can have also the y of t at 0 is 0. Same way, if I have y of lt, that means if I substitute x is equal to L here, that means L is cancelled out. We'll have sine n pi. And we know that the sine n pi is also 0 for all n. So that's why when we have x is equal to L, then also y of Lt is 0. And similarly, yt at Lt is 0. When t is 0, then y of x0, just observe that what we can have that. If t is 0, that means this quantity will become 1 and this quantity will become 0. So that means we can have, this is summation of bn sine n pi x upon L. So that means we have summation n running from 1 to infinity bn sine n pi x upon n. And this bn sine n pi x upon L, it is actually small u of x in the interval 0 to L. That's why this initial condition is also satisfied. If I have the derivative, that is yt at x0, when you differentiate this with respect to t, then this cos function will change to sine. And when you substitute t equal to 0 into the sine, this term will become 0 in that case. And here in this term, you will have this quantity is there which will change to cos. And that's why when you substitute t equal to 0, this value will become 1 and this will become 0 when you differentiate this. So finally what we can have is summation n running from 1 to infinity bn dash sine n pi x upon L, and L upon pi by c is already there. And this is the value which we have, it is v of x, which is between 0 to L. Therefore, we can say that this y of xt which we have achieved here, it satisfies the initial conditions as well as the boundary conditions. Let's see one example and we'll discuss the solution for that. The problem is solve del square y by del x square is equal to 1 by 4 del square y by del t square. If the value of x is between 0 to 2 and the t is greater than 0, we have given that initial conditions y of x0 is equal to x and yt at x0 will be constant. That means the velocity I am fixing as a constant where your x is between 0 to 2. And the boundary conditions are given, that is y of 0t, that means at one end point the displacement is 0 and the velocity is also 0 for any t greater than 0. So the problem is to find the solution for this. As we have discussed, the solution is written into this form. So for that we need to find out, here we have u which is x and here it is v is 2. So we need to find out what is the Fourier series for sine this function x and the Fourier series of 2. So now to find out the solution, we will find the Fourier series of u of x is equal to x in the interval 0 to 2 and v of x is equal to 0 in the interval 0 to 2. I should say it is a half range Fourier series because the interval is half. For that, let us calculate. We know that u of x is equal to summation n running from 1 to infinity bn sine n pi x upon L. Here the value of L that we have, it is here. So the value of L is 2. This will gives me where we know the bn, the value which is 2 by L, 0 to L, u of x sine n pi x upon L dx. So that's why it is, if I substitute 2 here, that will gives me 0 to 2 because 2 is cancelled out here. U is x sine n pi x upon 2 dx. Here I will use the integration by parts, and that will gives me x as it is. Integration of sine, we know it is minus cos n pi x upon L upon n pi by 2, minus the derivative of x, we know it is 1, and the integration of this quantity, it is sine, so it is sine n pi x by 2 upon n square pi square by 2 square, and the limit is from 0 to 2. Those who have not come across yet how to find out the Fourier series of given function, the video is already prepared for that. You can go to the I button and can watch how to calculate the Fourier series of certain function. And this will leads to the Bn is equal to, you just observe that if I substitute 2 here, this will be gives me cos n pi upon 2 n pi upon 2, 2 will get cancelled out, so we'll have cos 2 n pi, and this here will have a 2, so we can have that is 2 into 2 by n pi cos n pi, because this 2 goes in the numerator and this minus sign is also there. If I substitute 2 here, that will gives me sin n pi, and that is 0. If I put 0 here, this value is 0, and sin 0 is also 0. So that's why we can have only this term. So finally, what is the answer? We have it is minus 4 by n pi, and cos n pi we can write down it is minus 1 raised to n. So finally, we'll have minus 4 raised to n plus 1 upon n pi. So this is the value, that means the Fourier series x in the interval 0 to 2 will be summation n running from 1 to infinity 4 into minus 1 raised to n plus 1 upon n pi into sine pi x by. Calculate also the Fourier series for 1, the Fourier series, the half range sine series of v of x is equal to 1 is 1 is equal to summation n running from 0 to infinity b and dash sine n pi x upon L. L is 2, where the value of x is between 0 to 2, where bn dash is 2 by L, 0 to L, 1 into sine n pi x upon L dx. But the value of L is, as I know, it is 2, so it is 0 to 2 sine n pi x upon 2. If I integrate this, this will give me cos n pi x upon 2 upon n pi by 2 minus sine. If I substitute this limit 0 to L, if I substitute 2 here, then it will give me cos n pi. So it is minus cos n pi. When I substitute 0 here, will gives me minus 1. So it is minus plus become 1 upon n pi by 2. So the final answer for Bn dash will be 2 into 1 minus 1 raised to n upon pi. That will be the value of Bn. As per the previous discussion that we have discussed, that the solution for D'Alembert problem, that means this finite string, is written in this manner. That means we can write down solution given t, y of xt is equal to n running from 1 to infinity, then it is Bn. The value of Bn for this, we have got this 4 minus 1 raised to n plus 1 upon n pi. So it is minus 1 raised to n plus 1 upon n pi into 4. That is sine n pi by 2 cos pi t by, so it is n pi t we can write, plus 1 upon pi into 2, because c, the value of c is 2, so it is, I can write down it is 2 pi summation n running from 1 to infinity, the value of Bn dash The value of b n dash we got, it is this 2 into 1 minus minus 1 raised to n upon into n is already there into sine n pi by 2 into cos pi 2t by 2. So finally, if I simplify and remove this 2 and all sort of things, the solution is summation n running from 1 to infinity 4 minus 1 raised to n plus 1 upon n plus n pi sine n pi by x by 2 cos n pi t plus this 2 and this 2 is get cancelled out. So we'll have it is, and this pi and pi become pi square. So it is pi square summation n running from 1 to infinity 1 minus minus 1 raised to n upon n square into sine n pi x upon 2 into cos 2 will get cancelled n pi t. So this is the final answer for the given problem. That's it for this video. If you like this video, please press the like button. If you have any comment, suggestion or question, please drop down in a comment box below. See you in next video. Till then, bye bye.